Hello ma'am. Hello Radha ma'am. Shall we start?
Hello.
Yes, shall we start now?
Yeah, sure.
Okay.
Sure.
Uzma madam, please start the YouTube live session
Yes, ma'am. Wait.
so that we can start.
हाँ, ma'am. Yes. Yes, ma'am.
Yes.
Am I audible, ma'am?
Yes.
Your classes are also going still online?
Yes, ma'am. All the lectures are online still. Because hostels are not given ma'am yet, and many of the students are hostelites.
Okay.
Yes, Uzma ma'am, shall I start?
Yes, ma'am. You can start.
Okay. Good afternoon, all. I heartily welcome you all in the second session of this national webinar on partial differential equations, a geometric approach. The resource person for the second session is Professor Radha Madam, Professor and Dean, School of Mathematics and Statistics, University of Hyderabad. I heartily welcome you, ma'am, on this second session. I also welcome all the faculty members and the students who are present on this online mode for this national webinar. Actually, ma'am, the reason behind organizing this webinar is many times the students and other faculties are also unaware about how the solution behaves. What is the geometry behind the solutions of the differential equations as well. And since I have heard your lecture in the refresher course held in your university in July 2018. From then I was dreaming to organize your lecture for our students, and today is the luckiest day for all of us that you have with us in this online platform for giving us a lecture on this differential equation subject. Therefore, I behalf of Department of Mathematics, School of Computational Sciences, Punyashloka Ahiladevi Holkar, Solapur University, Solapur. I request Ms. Uzma Uchale ma'am to give introduction of the today's resource.
Okay. Today I am here for the introduction of our guest lecturer, Professor Radha ma'am. So firstly, I will say, Madam is working as a dean in the School of Mathematics and Statistics, University of Hyderabad. Madam has completed PhD from the IIT Bombay, that is in Indian Institute of Technology, Bombay. Madam has received fellowship from the CSIR, JRF, also from CSIR Research Associate. Madam has also received one more fellowship, Boyscast Visiting Fellow. Madam has a total teaching experience of 26 years, and out of that Madam is working as a professor from the year 2010, that is 2010, and Madam has a research interest in the partial differential equation and quasi-linear hyperbolic equations. Under the guidance of ma'am, one student has completed PhD and 7 students completed integrated MSc. Integrated MSc means MSc plus PhD complete. Madam
No,
has
sorry. IMSc means BSc plus MSc.
Okay, sorry. So BSc plus MSc. List of publications. So totally, ma'am has near about 25 list of publications, and madam is working as a many committees, like member of a local organizing committee of International Conference of Women Mathematician ICWM, member of local organizing committee of Advanced Instructional School on the Mechanics. It is supported by NBHM, and madam is working as a deputy director for the Center of Integrated Studies, University of Hyderabad, and madam is working for the coordinator of workshop on the partial differential equation and mechanics, and many more. So this is what a brief introduction of our today's guest lecture. Thank you, ma'am, for accepting our invitation. Thank you. Over to you, ma'am.
Thank you, Jyoti madam. Thank you, Ujma madam, for your nice introduction and for nice kind words that you have told about us.
Thank you, ma'am. And now I request you to please start the session.
Sure. Huh. So, first of all, I would like to thank you to Jyoti madam, and I also give my apologies that morning, though I have given my time, I could not be in but due to some official other commitments. Hmm. About
Fine,
the
ma'am.
participants now, are they your students? If they are, what are they doing? I would like to have the background of it so that I can start.
Students of our university department and some students are from the affiliated colleges as well.
Okay,
And all the students are from MSc 1 or 2 mathematics.
okay,
They have completed their course of ordinary differential equation in semester 1.
okay,
That of partial differential equation they have completed in their BSc, but little bit knowledge they have about partial differential equation. But for ordinary differential equation, we have a Coddington's book and we
okay,
have finished the paper.
okay. I'll start with a small question. If the participants can answer, please answer. Otherwise, I will continue. What is a differential equation? Ordinary differential equation. We'll start from there. Anyone can answer?
Yes,
Prof.
students are instructed to have a communication with ma'am.
Okay. Anyone would like to answer?
Yes, ma'am. The
Yeah.
equation in which derivative of one variable with respect to another variable which is independent is involved in that equation is called differential equation.
Right. Perfectly all right. Do you know what is a family of curves? Family of curves. Like we are having famous surname, family. They belongs to one family. Means all of them are having the same surname. In a broad manner, I'm just saying. Right? It could be surname, it could be father's name. So then we say that they belongs to the same family. Here, for curves, we are putting in a family. Belongs to one family. Okay, I'll give one example. Y equal to A into X. A is the parameter. Parameter means it can take certain values from the interval. In this case, A can take values from minus infinity to plus infinity. Y equal to A into X. The curves obtained from this formula, they are denoted as one parameter family of curves. Okay, so I'm trying to explain what is the family of curves. A function of x comma y comma one arbitrary constant is equal to 0 gives one parameter family of curves. So far, is it clear? So what is f here? F y minus a into x equal to 0. This is one example to say that to consider a one parameter family of curves. Right? Now, all these, okay, that means in a basket, we are having so many curves. One is y equal to x, one is equal to, and another curve is y equal to 0.1 into x, the third curve is y equal to 0.2 into x, like that. You keep varying the a value. since it involved only one parameter, that means what we are doing, we are trying to eliminate the parameter A in terms of the derivative. dy by dx equal to A, that A is nothing but y by x. Okay? So, a one parameter family of curves are represented by a first order differential equation. If you give me two parameter family of curves like y equal to c by y double dash plus y equal to 0. Right? So as the number of parameters are increasing, the order of the derivative is increasing. Clear? Is it okay? So what we are doing is, in a n parameter family of curves, we are trying to eliminate the parameters with respect to its derivatives. So we need n derivatives, hence it is represented by nth order differential equation. Right? In all these cases, the order of the derivative is n, but degree is also 1. So what happens when degree becomes 2? For example, dy by dx whole square is equal to something. The moment the degree becomes more than 1, that differential equation is representing not only one set of one parameter family of curves, it is considering the another set also. Right? In one basket, we have one parameter of family of curves. In another basket, we have another parameter, one parameter family of curves. But these two sets, these two baskets are represented by a differential equation, first order, but degree could be 2. Right? So as the degree increases, we cannot conclude how many curves it has, how many one parameter families it has a solution. Right? So geometrically you can imagine the curves are, the family of curves are represented by a differential equation. Right? So how do we solve the first order differential equation? Yeah, now I am coming to degree 1. Because in ODE, what we know is very little. In fact, we always think that, oh, if it is ODE, it is simple, PDE is difficult. No, even in ODE also we know very little. What is that little thing we know? If it is a first order differential equation of degree 1, even if it is a degree more than 1, using implicit function theorem, we can write dy by dx equal to this. So we can have n differential equations. Suppose a dy by dx that equal to f of the ODE has a degree k. That kth degree ODE of first order can be written as k first order differential equations of first degree. dy by dx whole square equal to say f. F is function of x and y. So dy by dx equal to plus or minus square root of f of x. So in principle, we maybe locally, though the differential equation has a degree k, I'll discuss with the degree 1 only. Okay, is it clear? Now when we come to the first order differential equation with the degree 1, do we know the solution? Do we have the method to determine that one parameter family of curves? No. In general, we have no idea. If f is arbitrary function, then there is no specific method, there is no systematic algorithm to find the solution. Then then what we do is, let us take the linear first order PDE. Y dash plus P of x into y is equal to Q of x. I think all of you can say that, yes, I can find the solution. Y is equal to constant times plus this. But here also we don't know the solution. But what we know is the solution can be written in terms of the integrals. Y is equal to constant times exponential minus integral p dx plus integral q into e, right? So that means the moment I give you a first order linear ordinary differential equation, you have the mechanism, you have the algorithm, you have the method to write y in terms of x, provided the integrals are known to you explicitly. Okay? So with this we conclude that a linear first order ODE can be solved, or we know the formula to find the solution of the first order linear PDE. The moment it is not, linearity is lost, then we don't have. Then what is the next step we can think of it? Anyone can tell me? What is the next step that we can think of it if it is non-linear? Right? I will share my screen. Hello?
Yeah, hello, ma'am.
Are you able to see the
Yes,
screen?
ma'am. Yes, ma'am.
Okay. Fine. So,
But your video, ma'am.
video will be lost. Once I use the
Okay. No issue, ma'am. No issue.
yeah. Y dash of x is equal to f of x comma y. This is the more general form that we use for the first order ordinary differential equation. First order ordinary differential equation of first degree. So now this I will write it as minus m of dy m dx. Okay. Minus n of x comma y divided by m of x comma y. So this means m dy plus n dx is equal. We write, and then this will be m only because I don't want to use the other notation. M dx plus n dy is equal to g. Okay? M dx plus n dy is equal to g. This all of you must be knowing. This equation can be solved if provided it is exact. That means what is the condition it should satisfy? dm by dy is equal to dm by dx. Exactness. Okay? So what is the meaning of the exactness? M dx, we can determine u, which is function of x and y, such that du is equal to m dx plus n dy, so that u equal to constant gives the solutions of the m dx plus n dy equal to g. Sorry, I am missing. Okay. Fine. So, under what conditions, if there exists u? So, under what conditions it exists? If this can be, the left hand side can be written as du by dx into dx plus du by dy into dy is equal to m dx plus n dy, which implies m is equal to du by dx and n is equal to du by dx. So precisely what we want to say, can I determine u such that its x derivative is my m and y derivative is my n? So we don't know whether it is possible or not. If I assume that, then the cross derivatives should be same. When I differentiate this with respect to y, this will be same as d square u by dx dy, which is equal to d square u by dy dx, which is equal to dn by dx. That's why we have the, if there exists u such that du is equal to m dx plus n dy, then dm by dy is equal to dn by dx. This is the fine. Suppose let dm by dy is not equal to dn by dx. Then what is to be done? I change the equation m dx plus n dy multiplying by some function where mu is a function of x and y. So if this condition doesn't hold, then the given equation is not exact. So what my intention is, I multiply by mu and assume that after the multiplying by mu, this equation is exact. Yes, assumption is this equation is exact. Okay, that means d by dx of mu into m is same as d by d, sorry, what was the dm by dy. So d by dy of mu m is equal to d by dx of mu into m. So further what we write is mu into dm by dy minus mu into dn by dx, that means that this has come from here, plus n into d mu by dx minus m into d mu by dy. Okay. So mu into dm by dy minus mu into dn by dx. So if I can determine at least one mu, then that mu is known as integrating factor. So for each mu, here one can determine this solution, family of curves. So how many, if we can determine more than one integrating factors, we can find more than one parameter family of curves. But the difficulty is how to determine mu. Okay, let us discuss case 1. Suppose let dm by dy minus dn by dx divided by n is a function of x alone. What is m? M is function of x and y. Are you able to hear me, please?
Yes, ma'am. Yes.
Okay. So n is function of x and y, n is function of x and y. So in general, this will be function of x and y. But if it is function of x alone, then what can we do it? So from here, what do you write? dm by dy minus dn by dx whole thing divided by n is equal to 1 by mu into d mu by dx minus m by n d mu by dy. Okay. So since the left hand side is function of x alone, I assume the right hand side is also function of x alone, implies mu is function of x only. Hence we get we get log mu is equal to integral 1 by n dm by dy minus dn by dx into dx. So the moment you know that whether this is a function of x alone, immediately one can write the integrating factor. Similarly, the case 2 is dn by dx minus dm by dy multiplied by 1 by m is function of y alone. Then mu is log mu is equal to integral 1 by m. This now you can calculate it how it has been done, dm by dy into d. Because it is function of y alone, so this term becomes 0. Mu is function, since dividing it by m, so here 1 by mu d mu by dy, the left hand side will be a function of y, and so mu is independent of x, so that can be calculated in this. Case 3, in the case of in this case, dm by dy minus dn by dx divided by y into n minus x into m is function of x into y. See, there is a difference. F is a function of x and y, x comma y. F is function of x alone, f is function of y alone, f is function of x into y. That means f is function of x comma y, f is function of x, f is function of y, f is function of x into y. Now I am talking about this. This whole thing is function. That means you can put x, y together. Wherever x and y are there, they are together. Suppose here x square plus y. This is x square y square. This is also function of x and y. This is also function of x and y. But this is a more specific form, xy whole square. Right? So in this case, our mu turns out to be log mu is equal to integral dm by dy minus dn by dx divided by y into n minus x into m d xi, where xi is equal to x and y. Because I am saying that this is function of x into y. Right? So how do we get this? Since this is the function of x and x into y, what I am doing is, in this, I assume mu is also function of x into y. So if mu is function of x into y, that is mu of xi, what is a d mu by dx? Is d mu by dxi into dxi by dx, which is equal to y. D mu by dy is d mu by dxi into x. So the substituting in that, you will get the integrating factor in this form. Right? Similarly, I will not give the further details, but for you to understand, you can verify the case 4 is if dm by dy minus dn by dx divided by y into n minus x into m y square, then is a function of x by y, then integrating factor log mu is given by dm by dy minus dn by dx y square by y into n minus x into m d xi where xi is equal to x by y. Case 5, I'll give only this is the last case that I would like to give it to you. If dm by dy minus dn by dx whole thing is divided by x into n plus y into m is a function of x square minus y square, then integrating factor mu is given by log mu is equal to integral dm by dy minus dn by dx divided by x into n plus y into m d xi, where xi is equal to x square minus y square. Okay? In this way, we have several special cases, but in general, there is no method. So, what we are doing, in fact, to solve the first order differential equation, ordinary differential equation, we have derived a partial differential equation. So, since we are not experts in solving the partial differential equation, we could see special cases and what cases it can be written, it can be reduced to the ordinary differential equation. That's what we understand. Okay? Then, so far, is it okay? Any doubts? You can stop me wherever you have difficulty. Hello? Hello?
Hello?
Uh-huh.
Yes, students, if you have any difficulties after this, you can ask.
No, ma'am.
Okay, fine. Now you understand how much we know about the first order, how much theory is known, how many ordinary differential equations of first order we can solve. Very little. Very little. Now we'll move to the second order differential equations. Right? So here we write d square y by dt square plus f of t into dy by dt is plus g of t into y is equal to 0. When it comes to second order, straight away I have written linear equation only, because in the first order itself for non-linear we had difficulty. So in the second order, whether can we solve all linear equations or not? Now tell me please, whether can we solve all these linear equations second order? That means, can we write y is equal to in terms of x, either in terms of the integrals? Can we? So, at least for first order differential equation, dy by dt plus p of t into y is equal to q of t. Here, in this case, we can write the solution in the form of, right, plus integral minus p dt integral q e power integral p dt dt. This we know. So even this much is also not known for linear in the second order. What we know is, in place of f of t and g of t, if they are constants, p naught dy by dt plus q naught into y is equal to 0. Yes, in this case, all of us, we can, for any given p naught and q naught, where p naught and q naught are constants, one can write the solution using the initial equation, which is equal to m equal to minus p naught plus or minus P naught square minus 4Q naught divided by 2. So I'll write these are 1 and 2, hence y can be written as C1 e power m1t plus C2 e power m2. So what we know is, if we have a second order ODE, then I am in position to write the second order solution of the second order equation with constant coefficients. P naught and Q naught are constants. Okay. So far is it okay? Since okay, under certain conditions, the even second order linear equations with variable coefficients, sometimes they admit a polynomial solutions, sometimes for certain cases. So there are, those equations are 1 minus x t square into d square y by dt square minus 2t into dy by dt plus n into n plus 1 into y is equal to 0. This equation, if you have done it, this is known as, you must be knowing as Legendre's equation. This is the linear second order equation. How many linearly independent solutions can be written? Okay, what is the meaning of the general solution? One of you can tell me? One of you can tell me what is the general solution? Huh?
Yes, students.
Please.
Yes, ma'am. A solution of a differential equation containing independent arbitrary constants equal in a number to the order of the differential equation is called general solution.
Okay. What I wanted to tell you is, especially for linear equations, P of x, P of t dy by dt plus Q of t dy by dt, y is equal to 0. Suppose I know y is equal to y1 of t as one solution. Y is equal to y2 of t is another solution. Now, I could determine only two solutions, two specific solutions. Probably you might have determined the third solution. Another participant has determined the fourth solution. But what we wanted to say is, if these two are linearly independent, any other solution can be written as a linear combination of these two independent solutions. In that case, we call this as the general solution. Okay, so here second order differential equation, so there are two constants, 100% correct. But what is the meaning of it? Since it is linear, if you take the linear combination, but the given differential equation satisfies, and this is known as general solution. That means if there are 100 many people, 100 many solutions are determined for the same differential equation, so those 100 solutions can be obtained from here by choosing C1 and C2 suitably. Is it clear? What is the meaning of the general solution?
Yes, ma'am.
So, in this case, in the Legendre equation, there exist two linearly independent solutions. How to determine those two linearly independent solutions? Do you know the power series method or Frobenius series method? How many of you know? Okay, if you don't know, don't worry, let us not. What I wanted to tell is, for this Legendre equation, when n is integer, when n is an integer, the solution, one solution of the Legendre equation is given by the derivation part. You not think too much, but you just try to understand 1 by 2 power n 2 power n factorial. Why I am writing this is a known form, so that wherever you see you can understand nth derivative of nth derivative of t square minus 1 whole power. See, this is the meaningful only when n is integer. So when n is integer, t square minus 1 whole power n is a polynomial of degree 2n. So you are differentiating with respect to n, hence is a polynomial of degree n only. Okay. Similarly, so this is known as Legendre polynomial. Legendre polynomial. So Legendre polynomials are widely used in PDEs, partial differential equations. Okay. The another example to find the series solution is t square d square y by dt square plus t into dy by dt plus x t square minus n square y is equal to 2. Again, when n is an integer, or for specific n is an integer, for this equation admits a polynomial solution. So what we are doing is to determine the polynomial solutions or any other solution, I will write, okay, here n is there, so I will write k. K is varying from 0 to infinity. I am assuming this series converges uniformly. So this is the first assumption that I am making. So that dy by dt is equal to the derivative, differentiation and infinite sum can be interchanged provided if this converges uniformly. So k is varying from 0 to n, 0 to infinity, m plus k into ak t to the power of m plus k minus 1. T to the power of m plus k minus 1. Okay. Similarly, y double dash also you calculate, substitute in this equation, collect the coefficients of like powers of t, so that you will get the constants ak and m also. So you get two m values, two values. So for each m you get one solution. So that is the series solution of the given differential equation. So far for second order differential equations, we know the solution means only this much. Second order series solutions, either polynomial solutions or series solutions. That means it contains an infinite number of terms. Infinite series solution we can pick up. That's all we can do, the maximum. Of course, so maybe if there are constant coefficients, then we can write the solution explicitly, very clearly in a well-known form. Otherwise, we can write it in the series form. Okay? Till now, is it okay? Till now, is it okay? Please let me know.
Yes, ma'am. Yes, ma'am.
So, further, I would like to mention that suppose I have the nth order differential equation, nth derivative of y plus f1 of t into n minus 1th derivative of t, n minus 1th derivative of y, and so on, f2 of t, n minus 2th derivative of y, and so on. Lastly, we have Fn of t into y. So, since I cannot find the solution of it, I have something in my mind. Can I see this nth order ODE as in terms of the first order ODEs? The answer is yes. Suppose I'll put dy by dt is equal to x1. D square y by dt square is equal to x2, which is equal to dx1 by dt. Like that, nth derivative of y is denoted by xn, which is nothing but first derivative of xn minus 1. Okay, so from here what can you see? Dx1 by dt is equal to x2, dx2 by dt is equal to x3, and so on. Dxn by dt is equal to minus f1 of t here, and n minus 1th derivative of y is xn minus 1, and f2 of t xn minus 2, and so on. So what I am trying to do is d by dt of the vector x1, x2, and so on, xn is equal to matrix multiplied by x1, x2, and so on, xn a11 of t, a12 of t, and so on, a1n of t. Similarly, an1 of t, ann of t. Okay? So, the nth order differential equation can be seen in the form of a matrix. So, for example, if I put capital X as x1, x2, and so on, xn, dx by dt is equal to a into x, where a is a matrix function of t, right? So far we have not learned anything, but what we have done is, if we have any nth order ordinary differential equation, that can be seen as in the form of dx by dt equal to a of t into x. Okay? So far is it clear? Any nth order ODE can be written in terms of this. So again, it is just a representation, but what I would like to do is, here a is function of time t. In place, if this is the constant matrix, then what happens? Okay, now I'll take only two variables, x and y. Dx by dt and dy by dt. So what you could understand here is, any nth order differential equation, linear differential equation, can be written in this form. But what is the more general form is dx by dt equal to f of x comma y comma t. Dy by dt is a function of x comma y comma t. That means, if under certain cases, this represents the second order ODE, right? So now further, I'm reducing the complexity of the I'm relaxing the certain by putting some more conditions. That means, if I remove t, then this is known as autonomous system. This is known as autonomous system. First, I will discuss about the autonomous system. Dx by dt is equal to f of x comma y dy by dt is equal to g of x comma y. So what is the first one? Dx by dt is equal to f of x comma y comma t. Dy by dt is equal to g of x comma y comma t. We are not able to say anything about it, so I have reduced I have removed the one variable t, so that this is the autonomous system. Further, I am reducing dx by dt is equal to a into x plus b into y. Dy by dt is equal to c into x plus d into y. Okay, that means even this also I'm not able to handle it. Why we are simplify whenever if that is a difficult for us, we put some more assumptions and try to reduce it to the known form to us. So for me at present, if f is arbitrary, g is arbitrary, I cannot handle it. So but when f and g are linearly depending on x and y, then I can write this. Okay, so that can I write the solution of this differential, this system of autonomous equations? The answer is yes. Can I write it? Any of you can answer me whether you have solved this kind of equations or not? Hello?
Hello, students.
Have you done it or not? Just let me know.
Yes, ma'am, this was included in the syllabus.
Okay, very good. Very good. So, what is the meaning of it? Dx by dt is equal to a into x. So, we consider the one arbitrary vector into e power mt. It turns out to be m is the eigenvalue of a, and c1 comma c2 is the corresponding eigenvector. Okay, corresponding eigenvector. So in this case, that means for a given matrix A, you determine the eigenvalues and determine the eigenvectors, so you can write this solution. So if for time being, I'll stick to A is 2 by 2 matrix. So M1 and M2. X comma. X, when I put capital X equal to 0, left hand side is 0, right hand side is 0, hence it is a solution. Okay, but at the same time, this system has a general solution of this. Okay, have you done the stability analysis?
No, ma'am.
No.
Not there in the syllabus.
Okay. So now I'll go little slowly. About it. Right? So this is the, if matrix A is given, immediately you can say that the solution of this system is given by this. Okay. Now the question is, dx by dt is equal to ax plus by, dy by dt is equal to cx plus d into y. D into y, yeah, this is not the derivative. Okay. What is dy by dx? Is c into x plus d into y divided by ax plus b. Okay. Here you should understand, I have to go very slowly. The solution of this system can be written like this. Y is a function of x. This is one solution, this is another solution, this is the third solution, like that. So dy by dx is given. I can write the solution. Whereas the solution of this is given by x is x of t, y is y of t. It is in the parametric form. So t is varying from minus infinity to plus infinity. For a given t, I can calculate x, I can calculate y. As t is varying, I can calculate x and y. So I can plot them in the xy plane again. X equal to x of t, y is equal to y of t. Do you see any difference between this and this? In principle, no. The solution of these curves are given by this. The solution of these curves are also given by this. Are they one and same? That is the important thing. Are they one and same? As a curves, they are one and same. My answer is, as a curves, if you plot the curves in the xy plane, that the same thing by eliminating t, this can be written as y is f of x, which is a solution to this equation. But these curves will tell us something else also, something extra. What it is? If I say that it's a solution, maybe y of x naught is equal to y naught, so I'll call this as x naught comma y naught. I'm determining, since this equation has infinitely many solutions, out of that I'm picking up only one solution or one curve passing through x naught comma y naught. Okay. Similarly, here also x equal to x naught when t is equal to t naught, y is equal to y naught when t equal to t. So again in the xy plane, I can identify a point x naught comma y naught, so I get one. So what's the big deal? What way it is different? Now I'll take. At t equal to t naught,
Hello.
let us assume the particle is located here. So x equal to x of t, y is equal to y of t is the coordinates of one particle. At t equal to t naught, the particle is located at x naught comma y in the xy plane. As t increases, x is changing, y is changing, right? X is changing, y is changing. So whether at t equal to t naught, as t greater than t naught, whether the particle can move in this direction or in this direction when t is greater than t naught. So the difference between these two things, here they are curves. The curves are known as paths and they are with direction. So if you solve this system using this equation, you get only the solution, curves in the xy plane, but you don't get any directions. Whereas if you solve them as a system, you get the directed paths. So these are the directed paths. The second point is no two paths can intersect. No two paths can intersect. Anyone can tell me why? So the question is x, y plane. This is one path and this is another path. Can they intersect at alpha comma beta? This path is having the coordinates x0 comma y0, x1 comma y1. Now at this point, both, that means x of t, y of t, they can take the same values at different times as alpha comma beta. Okay. The answer is this is not possible. Why? If it is possible, what is the slope of this path? Is divided by dx. What is the slope of this? Is divided by dx. But we have only one slope. Divided by dx is uniquely mentioned. Hence, no two paths can intersect. Okay. With this, I'll proceed further. Further, again I will write dx by dt is equal to ax plus by, dy by dt is equal to cx plus dt. So, as I mentioned, x comma y can be written as c1 into alpha 1, alpha 2, e power m1t plus c2 beta 1, beta 2 into e power m2. Assuming that m1 is not equal to, they are distinct. If they are distinct, and let m1 is positive, m1 is negative, and m2 is also negative. So what happens to x value, y value as t tends to infinity? You should be able to answer me. You should be able to answer me that what my question is, if m1 and m2 both are negative, then what is the value of x as t tends to infinity? Tell me, as t tends to infinity, what is e power m1 into t? What is e power m2 into t as t tends to infinity?
0.
0. So that means in this case, if m1 and m2 are negative, all the curves are approaching to 0. But just now I said that no two paths can intersect. I take c1 comma c2, one set of values, I calculate the curve, I draw the curve and see that as t tends to infinity, it is approaching to 0 comma 0. Take some other c1 and c2 as t tends to infinity. So for all C1 and C2, limit of x is tending to 0. I mean, limit of x as t tends to infinity is 0. Limit of y as t tends to infinity is 0. Then am I contradicting to myself that the point 2, that no two paths can intersect? No, I am not intersecting to myself. Means this is not the contradiction to this statement. So what does it mean? Intersecting means after intersecting there is a path, but here the path ends at this point. That means if it starts from here, as t tends to infinity, it is here. After that there is no path. As t tends to infinity, similarly if it starts from here, as t tends to infinity, it is reaching here. So don't think that this path is extended like this. So for example, all these are paths, but all these are intersecting at this point. Means this is one path, this is another path, third, fourth, fifth, like that. The path is not extended after passing through G. So that's why we say that as x t tends to infinity, x is tending to 0. Once t is tending to infinity or reaching to 0, there is no value for t. That is ultimate value. That is ultimate value for x and y. Hence, after that there is no, the curve is not continued. Hence, there is no question of crossing two curves. That doesn't happen. In that sense, I am not contradicting to my statement that there is no two paths can intersect. Okay. If M1 and M2 are positive, say, if M1 and M2 are positive, then what happens? If M1 is positive, M2 is positive, then what happens is y equal to limit of x as t tends to minus infinity 0, limit of y as t tends to minus infinity 0. So when both are positive, as t tends to minus infinity, this will be 0, this will be 0, again etc. So always we mention in this, all paths are approaching to 0, 0, either when t is tending to infinity or when t is tending to plus infinity or minus infinity. Further, I will write x equal to c1 into alpha 1, alpha 2 e power m1t plus c2 into beta 1, beta 2 e power m2t. What are m1 and m2? m1 and m2 are the eigenvalues of the matrix A. Alpha 1, alpha 2, beta 1, beta 2 are the two eigenvectors in matrix. Matrix A corresponding to the eigenvalues m1 and m2. So since I can choose x0 and y0 such that my c1 is non-zero and c2 is equal to 0, I always can choose, right? So once c2 is 0, what is my x? X equal to c1 into e power m1 into t alpha, y is equal to c2 into m1 into t alpha 2. So from here, can I write y by x is equal to, y by x is equal to alpha 2 by alpha 1 implies y equal to alpha 2 by alpha 1 into x. So alpha 1 and alpha 2 are the components of the eigenvector. So this will be the solution implies this is one solution, this is another solution. Y equal to alpha 2 by alpha 1 into x, one solution, and this is also the same solution, but how do we write it? X equal to alpha by c1 into, that means x equal to c1 into e power m1 t alpha 1, y is equal to c1 into e power m1 t alpha 2. Whereas the second part, this part can be obtained as x equal to minus c1 into e power m1 t alpha 1, y is equal to minus c2 into e power m1 t alpha 2. Okay? So, this is one path and this is one path. They are meeting at this point. They are approaching. Finally, they are meeting at that point. Right? So, now this path, if m1 is greater than 0, okay, first I'll take m1 is less than 0, m2 is less than 0, this path is moving towards this direction, this path is moving towards this direction. Similarly, when alpha equal to beta 2 by beta 1 into x, I get another line. So this is another path. So these are the four paths. These are the four paths. What are these four paths? Depending on m1 and m2, which are not equal to 0, but m1 into m2 is greater than 0. That means both are having the same sign. Okay, here I will put that m1 is less than 0, m2 is less than 0. Till here is it okay, please? Please tell me.
Yes, ma'am.
Now, see, these four paths we have determined such that C1 is not equal to 0 and C2 equal to 0. The second one is C1 is equal to 0, C2 is not equal to 0. So, I have chosen x0 and y0 such that I obtain these four paths. If I choose some other x0 and y0, that means say here x, y. If I choose some other point, if the path, that means the curve, that we have identified four paths. Now, at any other point, if I determine the path, that means the path passing through a point lying between these two straight lines, that will be lying inside this region only. That means the xy plane is divided into four regions. This is the first region, second region, third region, and fourth region. If the curve starts in the first region, for all values of time t, it will be in the first region. What does it mean? Why it is so? Can you tell me? What does it mean and why it is so? Suppose x equal to x of, so I will determine x equal to x of t, y equal to y of t, such that x of t naught is equal to x naught, y of t naught is equal to y. If I determine the solution subject to this condition, then I can, by eliminating t, I can draw a curve in the xy plane. So the curve should pass through this point. Am I right? If the curve passes through this point, the curve will be here only. That means that the curve cannot cross this line. Why? If it crosses at this point, these two are having the different slopes. which is not allowed. So this analysis will tell us that if I have determined four paths when M1 and M2 are distinct and having the same signs, so this will be one region. In this region, if the curve is could be like this. In this region, if x naught is there, so the curve will be like this. It cannot enter into the other region. So an entire xy plane is divided into four parts. In each part, if the curve is located at some point t equal to t naught, for all time it will be in that region only. Is it clear? Please tell me.
Yes, ma'am.
Are you sure?
Yes, ma'am.
Okay, good. So this analysis we could do it only when M1 and M2 are distinct and having the same sign. That's what we could do. When M1 and M2 are equal, then what can we say? Suppose M1 and M2 are equal. Say dx by dt is equal to a1x plus ax plus by, dy by dt is equal to cx plus d into y. Okay. Let M1 is equal to M2. So what is M1? M1 is the eigenvalue of the matrix A, B, C, D. So when both the eigenvalues are equal, we may have two linearly independent eigenvectors, or we may have only one linearly independent eigenvector. So for example, if I take 1, 1, 0, 1, here lambda equal to 1, M1 is equal to 1, M2 is also equal to 1, we have only one eigenvector, 1, 0. Suppose I take 1, 0, 0, 1, M1 is equal to 1, M2 equal to 1, but here I have two linearly independent eigenvectors. Okay, when M1 and M2 are equal, if there exist two linearly independent eigenvectors, we have no problem. C1, alpha 1, alpha 2, e power mt, m1t plus C2, beta 1, beta 2, e power m1 t. Again, no problem. But if m1 is positive, limit of x comma y as t tends to minus infinity 0, and m1 is negative, limit x comma y as t tends to plus infinity 0. So in this case also, we will be having the two lines, two curves. So that means by putting C2 equal to 0, I get one straight line. By putting C1 is equal to 0, I get another straight line. So both the things to be. So the given region is divided into, xy region is divided into four parts, and so the analysis will be the same as when M1 and M2 are distinct and have the same sign. But when M1 is equal to M2, but A admits, with one eigenvector. In this case, what is to be done? So I have one solution, x comma y is equal to C1 into alpha 1, alpha 2, e power m1 into 2. What is the second solution? Because since it has two equations, I need two linearly independent solutions. So this is one solution. What is the another solution? The another solution is K1 k2 into t e power m1t. What is this? This is the one is the eigenvector and the other one is the generalized eigenvector. So what is the generalized eigenvector? A into x is equal to m into x. X is the eigenvector, right? A minus m into I, y is equal to x. So here you can see that it is a singular matrix. So this y is known as generalized eigenvector. Generalized eigenvector. So once we know the generalized eigenvector, we can write the solution in this form, which are both linearly independent. Okay. The third one is m1 is equal to alpha plus I beta, xi plus I eta, and m2 is equal to xi minus I. While writing this, I have assumed certain thing. What is that? A is the real matrix A, B, C, D. A, B, C, D are real constants. In that case, there exists a possibility that eigenvalues could be complex. If one is complex, the other one is the complex conjugate. So, correspondingly, the solution x comma y can be written as e power xi t plus I eta t plus c2 again vector e power xi t minus I into eta t. So what I would like to do is c1 into matrix e power I theta can be written as cos theta plus I sin theta. So I'll write this e power I eta t into this in this matrix form. So e power xi t plus c2 into something e power. So this whole thing into e power xi t, right? So now here xi could be positive, xi could be negative. If xi is positive, then limit of x comma y as t tends to infinity is 0. If minus infinity. So if xi is negative, limit of x comma y as t tends to plus infinity is 0. Okay. Now very nice. So in all the cases, m1, m2, whether they are positive or negative, or they are having opposite signs, what we understand is either with t tends to plus infinity or with t tends to minus infinity, all curves are approaching to 0, 0. Now we'll analyze. What is m1 and m2? It is a minus m, b, c, d minus m is equal to 0. Determinant of this matrix is 0. So m square minus a plus d into m plus ad minus bc equal to 0. So m equal to a plus d plus or minus square root of a plus d whole square minus 4ad minus bc divided by 2, which is equal to a plus d plus or minus, this can be further simplified as a square plus b square plus 2ad minus a minus b whole square. Now let it be as it is. I will put it in the same form. ad minus bc divided by 2. So if this term that is known as a discriminant, if the discriminant is positive, we have two distinct eigenvalues. m1 is not equal to m2 when a plus b whole a plus d whole square minus 4AD minus BC is positive. So that means M1 is positive, M2 is positive, or M1 is negative, M2 is negative, or M1 is positive and M2 is negative, or M1 is negative, M2 is positive. Okay. If these two values are, if M1 is positive, M1, then immediately can I conclude that M1, M2 is positive? M1 plus M2 is positive and M1, M2 is positive. This implies M1 plus M2 is negative, M1, M2 is positive. This implies M1 plus M2 can be anything, but M1, M2 is less than 0. Right? But what is M1 plus M2? Is nothing but A plus B. What is M1 into M2 is, what is M1 into M2 is yeah, M1 into M2 is AD minus BC. AD minus BC. So we can conclude that if A plus B is positive, AD minus BC is positive, A plus B is negative, AD minus BC is negative, positive, and AD minus BC is negative. 3 cases. So A plus D positive, AD minus BC positive, A plus D negative, AD minus BC positive, AD minus BC negative. In this case, M1 is greater than 0, M2 is greater than 0. In this case, M1 is less than 0, M2 is less than 0. In this case, one of them is positive and the other one is negative. Okay. So far what we have done, we have observed that in this case, we have the 4 regions and the solution can be taken. These are the regions, the solutions are approaching, right? Right. So this point is called as a node. I'm introducing one new word. I'm introducing a new word. So, okay, even if you don't understand node, it is okay. But what I would like to say is, if limit of x comma y as t tends to infinity is equal to 0 comma 0, what is 0 comma 0? All curves are approaching the one point, so that is 0 comma 0. Then 0 comma 0 is said to be asymptotically stable point. In fact, here I should use the word critical point. What is a critical point? A point solutions are known as critical points. In this example, 0 comma 0 is the only point solution, means constant solutions. So since 0 comma 0 is the only constant solution, that solution is known as the asymptotically stable point. If I don't think I can complete the entire thing, then 0 comma 0 is said to be asymptotically unstable critical. Okay, now I'll not write anything, I'll try to explain it a little bit. Yeah, I have written so much probably. What we have done is, for a system, I have to cover why we have considered the linear system. So when we consider the linear system, we could see that as t tends to infinity, all solutions are approaching to one point. Either t tends to infinity. As t tends to infinity, if they are approaching to 0, 0 means as t increases, they are moving away from the origin, from 0, 0. So when all are approaching as t increases to infinity, that is called as attractor. As t tends to infinity, if they are moving away, implies as t tends to minus infinity, if they are approaching the same critical point, that is known as repellent. One small example I would like to. In a sink, in a wash basin, if you pour the water in the wash basin, what happens? Wherever it starts, it will enter into that. The outlet. Whereas in a fountain, if you look at the fountain, the water is throwing out. It's throwing out in different directions. So this point is a repeller and that point is a attractor. If you take a bowl, take a bead, leave it on the surface of the bowl, what happened? If the bowl is like that, it will ultimately reach to the bottom point. Wherever you leave it, it takes its path, it will move, approach to that point. So as t tends to infinity, it is approaching to the bottom of the bowl, so that point is a attractor. But same thing if you put it in the reverse way. The ball is an inverted ball. It is an inverted ball like this. Wherever you put, it will move away from that. That means as t tends to infinity, minus infinity, it might have started from there, but finally it is moving away from it, hence it becomes a repeller. Right? Is it clear? Probably I should stop at this level. I don't know whether I have met the Jyoti madam's expectations or not.
Yes.
Right.
Yes, ma'am, surely.
Yeah. Any questions, please?
Yes. Students, if they have some questions, they can ask.
But we feel more happy if you ask questions.
Yes. And actually, you are focused on many aspects of ordinary differential equation. Some of them are not known to me also. At last points, maybe due to a very large gap when I taught my ODE paper and now, I forgot some points.
What is? Acha, okay.
But you have covered much of the points.
Okay.
Yes,
okay. So questions,
please.
please. Questions, please. You concentrate on one small topic and raise your questions.
Yes. Anyone from students have the questions? Ma'am, I have a question.
Yes.
Whatever the general solution we were thinking, suppose it is of two parameter general solution, and if I go or switch to a particular solution, that will be also a family of curve. Can we say the particular solution will be a subset of general solution?
Particular solution? Yes, only one solution. But
one solution.
Yeah, it is. But here I have to be little careful. Whatever statement I make, that is true only for linear equations. For non-linear equations, it is a different.
For non-linear, it behaves differently, no?
Yes. For non-linear equations, it might admit one general solution. It may not admit only one general solution. It may admit so many general solutions. Not only that, there are some specific solutions which do not belongs to any of these families. So those are known as singular solutions. So non-linear differential equations is entirely different.
Can we say same about one parameter family of solutions, whether it is a subset of two parameter family of solutions?
Yes.
Now it is a subset relation.
For linear.
For linear only, yes.
Again for linear.
Only for linear.
Yes.
For non-linear, actually it is going to be somewhat difficult solutions part.
Yes. First
we
of
have-
all, we don't know even if a second order linear equation, how many general solutions are that also we don't know.
Yeah, we don't know.
And are they complete? That also we don't know. There could be some solutions upon which are not allowed in these baskets. They are not able to find from these baskets.
That's why personally I feel, ma'am, solving differential equation is very easy. Solving the problems, finding their solutions. But understanding the theory, the geometry behind those is very important.
Yeah,
Rather bit difficult.
yeah, this is the last example I have considered because though it looks linear, but so much complications are there. So if it is a non-linear equation, how can we think of it?
Yes, ma'am. It's not possible. I think
That's-
those questions were going to research level.
Yeah.
Maybe. Yes? Anyone from students? Having their questions, faculty also can ask.
In the feedback, you please write your real opinion. Just don't say that wow, lecture is good. That is, no. We want real things so that we also can improve from our side.
Surely I'll share you, ma'am, with you the feedback.
Okay.
Actually, I'm from the bottom of my heart. I'm very thankful, ma'am. You have given your valuable time to us. You have shared your valuable thoughts on this topic with us. I'm very much thankful. And now, I hope there are no questions from student side. Okay. This is a bit difficult situation
Yeah.
actually.
Next
in
time
online.
when you organize something, you tell them that if you don't raise the question, they won't get the certificate. Then
Yeah, sure.
they try to find ask questions.
Sure. And next time, ma'am, surely we will call you when everything will be in physical way. Instead
Sure.
of online, we will be very happy if you come here and you guide us.
Okay, fine.
Okay. Now I request Mr. Vinay Kandi sir to put vote of thanks for this session.
Okay, ma'am. So, good afternoon to one and all gathered here on this wonderful evening. I would like to present the vote of thanks. A national webinar on partial differential equation geometric approach, organized by Department of Mathematics, School of Computational Sciences, Punyashlok Ahilya Devi Holkar, Solapur University, Solapur. So, I would like to thank our beloved VC ma'am, Dr. Hunalini Fadnavis ma'am, for giving permission to arrange this webinar. And I would like to thank our resource person, Dr. R. Radha ma'am, for accepting our invitation and giving such a nice lecture on geometric approach of a differential equation, on a differential equation. And I would like to thank our director of the school, Professor Dr. V.B. Gutesar, and the head Department of Mathematics, Dr. J.D. Machari ma'am, for organizing this webinar. So I would like to thank all the staff members, students, teachers, and participants. Once again, one and all present here, I would like to thank. Okay, over to you, ma'am. Thank you.
Okay.
Thank you, sir. Thank you, ma'am, again.
Thank you, Jyoti madam. Thank you, sir.
Thank you, ma'am.
Thank you, ma'am. Okay, ma'am. I
Okay.
end up the meeting. Thank you.
Sure. Okay, bye. Good luck to all participants.
Thank you so much, ma'am.
Thank you, ma'am.